Observation stored. Target locked. Observation stored. Target locked. First phase completed. Target locked. Observation stored. Target locked. Observation stored. Target locked. Round completed. Changing face. Target locked. Observation stored. Target locked. Observation stored. Target locked. First phase completed. Target locked. Observation stored. Target locked. Observation stored. Target locked. Round completed. Changing phase. Target locked. Target locked. Observation stored. Target locked.
Hello again. It's a lovely morning here. I'm going to be testing some new equipment and doing some configuration of some new equipment today. And I thought I'd take advantage of the opportunity to set up a little test range for that purpose, but also to record some of the measurements to demonstrate how surveying measurements, how the Theodolite takes advantage of perspective and actually records the lines of perspective to the objects that you're measuring to. This came up because I've seen memes and commentary on the internet regarding perspective and convergence and the vanishing point and things like this, related to some effect that this has on surveying measurements to cause them to be somewhat flawed or inaccurate, or other claims I've seen. I mean, just basically that perspective somehow makes surveying instruments inaccurate. So I think through this test you're going to see that it's quite the opposite. Surveying measurements actually are measuring the perspective. And in fact, later in this video I will insert some information about an old piece of technology called the subtense bar, and I'll talk more about that too. So if you've seen my videos, you've noticed that I'm always using this optical mechanical theodolite. It's called a T2. It's a 1 arcsecond instrument, and you know, it basically measures horizontal angles and vertical angles. Okay, and it does not measure distances. There are no electronics in this instrument. In fact, you have to do a lot of hand recording of what you're actually measuring. Let me just set this down. So you've also seen in my videos or on my blog where I've posted pictures taken through the telescope to show you the crosshair, on certain objects. In fact, I've actually set the instrument to be level, okay, and recording photographs through there. It's not hard. It's hard to do. I've done it, but in fact, it's right here. Actually, I'm not going to do that, but I'll insert into the video here some pictures that I've taken of the Empire State Building from 41 miles away, on top, from sitting on top of the lighthouse at Fire Island on Long Island. Then I went to the other side of the city and took pictures from a park called Washington Rock. I've taken pictures along the Delaware Bay of lighthouses, 14-foot bank light, Brandywine Light, and some other lighthouses. Also, Cape May Lighthouse from across the Delaware Bay on the Delaware side, looking toward New Jersey. Now, when I've posted these, this is when I've actually encountered people, raising this issue that these photographs are flawed due to perspective. And I hope that throughout this video you're going to see that that is not the case. Now, one of the things that I could not take pictures of is through this little telescope, which is it's very small. I can't get my iPhone up to that. This is the readings that I record. And what happens is there's a glass circle in here, and you use this mirror to let the light in, and you can literally see the readings here, and that's how you record that. And so for this test, T2 is going to sit this one out and just kind of watch. What I'm going to use is just this electronic instrument. And the advantage to this one, of course, is that it measures distances. Now, so this is a digital theodolite. It's a 1 arcsecond theodolite, but it measures distances. And I'm going to need to record distances on this test, because what you're going to find out is that the angular differences will get smaller and smaller and smaller the further and further and further away you are. So let's look at the setup I have. I've got two targets. These two targets are the same size, actual same make and model targets. And I've dug up this geodetic monument. It's called, let's get it, zoom in on here. I'm too close. You can see that it's 4G1, set in 1999 by the New Jersey Geodetic Control Survey. And what you do is, this is an optical plummet. It has a prism in here, and it lets you set up directly over the mark. And I've aligned this ruler directly over the mark. And it's a metric ruler. It's It's also in feet on the other side. And I've taken pictures of all this. So basically I've set this spike 2 meters away. Again, I've taken pictures through here and I'll insert them in the video to show you that I'm actually over that mark. And I'll also insert the pictures showing you how I've measured the height of the target above the geodetic monument and the height of this target above the spike. And with that information and the measurements that I'll make with the theodolite, I'll be able to compute the position of this target over here based on this known set of three-dimensional coordinates: northing, easting, and elevation, or otherwise latitude, longitude, and height. And that's going to be the purpose of the test. Now what you'll notice is I've set up some spikes online. I just eyeballed these. They're not surveyed or laid out or anything. I just eyeballed, just lining that up like that. Okay, and then I'll have another one over here. And there's one there, and then of course I put one across the street, and then there's one further down. So there's 5 spikes, and the 5th one is down by that bench. Right down there. So, I'll record video at each station. The idea is that what I'll be doing is setting up the instrument at each one and measuring the relationship between the 2 targets. And, you know, as you can see, from here, those 2 targets look closer together and very small. That's what perspective does. Perspective is a visual thing. It's not anything that actually affects dimension or spatial relationship. So, you know, I keep seeing these memes talking about what we see with our eyes, and from that standpoint, they're correct. The closer you are to something, the larger it gets. Okay? The farther away you are from something, the smaller it gets. But that doesn't mean it is really smaller, and it doesn't mean that that distance is not 2 meters. It is 2 meters. Whether I'm there or here, it's still 2 meters, not 3 inches. Alright, we've got some preliminary results of the first setup. Instrument is at 0.1, measuring back to 5 as my back sight. You can see the residuals of the 4 sets are quite small, down in the 1 and 2 second range. And the distances were flat except for 1 millimeter to number 6. I'm calling the target there on the left number 6, and that is called 3G1. Alright, so that's what it looks like after the 4 sets are completed, and then I'll close it and store them.
Observation stored. Target locked. Raise wing up. Round completed. Changing phase.
Alright, now I'm at point 2, measuring a set between those two, and also to my next setup, point 3. This should go pretty quickly. Look how small they are already. They're so small.
Observation stored. Target locked. Observation stored.
Well, there's the results of this last set here at Station 5, measuring between the two targets way, 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 way back there. I had to turn these manually, and that's why I couldn't video the robot turning, because I was turning it. And the reason for that was that because of how close together they are, way, way, way back there, I was getting a return from both prisms, and it couldn't distinguish which one to lock onto. So I turned that feature off and manually pointed them myself and recorded those observations. So that's the only difference here. I took it off of the automated mode and did my own pointings, which are definitely comparable to the results of any of the others. All right, so I think there's one more setup. What I'll do next, I haven't done this yet, I should really sit on the geodetic monument, backsight this point, and turn an angle and measure the distance to the target that is 2 meters away. Hopefully that's not inside of the there's a range limit on this. I mean, it won't measure. This thing will not measure a distance, too close. And I forget what it is. 2 meters might be too close. We'll find out. But anyway, we'll give it a shot. Okay, I've got about 5% left on my phone battery. Need to make this quick.
No target. Target locked.
I'm quite pleased to know that I can measure the distance, this short distance. So we're going to measure these 4 sets here, backsighting Station 5.
No target. Target locked.
A lot of traffic coming now. Alright, I think that'll be the end of the video here in the field, collecting the measurements. The rest will be later on, putting it all together. Talk to you then. Alright, I'm recording just a quick little video clip to mention the fact that the monument that we started from is called 4G1. I have been writing 4G1 for my occupation records and up measurements, but in the data collector, I've been keying in 3G1, so I'll just be editing that, and I just wanted to make mention of that edit that's needed to be made. Wow, look at that perspective. Perspective, baby. All right, and here's what we've all been waiting for, the final results, right? So I've been thinking about how to display or present the final results, and this was the easiest way that I could think of, just to report out the mean angles at each station. So the first one at station 1, backsighting 6, the target that's 2 meters away from the geodetic monument 4G1. These are the sets. I turned 4 sets in phase 1 and phase 2. And so here's the average in bold, the standard deviation, and then here's the vertical angle and the standard deviation, and the distance in meters in the standard deviation. So there's station 1, and that's the angle between 6 and 4. And then same thing, a little bit further away, here at nearly 18 meters away. You can see already we're measuring a much smaller angle. Standard deviation, and that's from station 2. And then a little further away again at station 3, the angle's getting smaller. And now we're going to go across the road to station 4. The angle is definitely getting smaller, as you can see. And there I am across the road. And the last station at station 5. We're under a degree. We're just about 40 minutes almost in horizontal angle. All right. And thought I'd just also include the positional tolerance of 0.6 after making all of these measurements in meters, 5 millimeters by 4, and about a centimeter in elevation. And that's at 95% confidence. And I figured I would just tabulate here all the points with their coordinates and their positional tolerance at 95% confidence. And drum roll, what's the distance? 1.998. So not too bad for just laying a ruler down and plumbing over the 2 points that way. I guess it says a lot about the wooden ruler. It's almost 2 meters within 2 millimeters. And I think that's it. So I think that's all there is to say about how measurement actually takes advantage of perspective using a surveying instrument. I think what I'll do next is address some of the memes that I've made some copies of. So I'm going to do that next. All right, this is the part of the video that I will talk about some of the graphics and memes that you see out here. I just did a search on perspective flat earth, and you can see there's tons of these out there. But after watching the video that you've just watched, I hope you noticed that perspective really has no effect or influence on the measurements, on the results of the measurements. Whether you measure something close up or measure it from far away, you're going to get consistent, repeatable results. And that's just the way things work. All of these have to do with appearance. It's a visual thing. I mean, it's like, why go to all this effort to create all these graphics to talk about something that is like so common, so well known. I mean, geez, yeah, this telephone pole looks really big when you're near it, and they appear to get smaller and smaller. But if you walk along here, you'll notice that the poles are all the same size. What are you talking about here? Just stuff astounds me. I really don't know what to make of it. Most of the stuff having to do with surveying that you'll see is absolutely false and wrong. I think most of it comes out of that Samuel Robotham's book. So, believe that stuff if you want to. But, I'm here to tell you that surveying and the use of a theodolite is not affected by perspective. And I think I made that point in this video. I've shown you that. So with that information, I hope you'll go back and if these types of memes made sense to you before, you should really start questioning this. These things are just all about a visual appearance. The size of this box doesn't change because you slide it down along these lines. The box is the same size, literally. I didn't even discuss the vanishing point because there was really no point to it in terms of surveying, because we can only measure the things that we see. So anything that I'm measuring to, I can see it, and so it is not beyond the vanishing point. Got to start thinking about this stuff, and don't get taken in by I don't know, this is like sleight of hand and magic to me. Perspective. No kidding. Hey, you know what? Here's what I'm going to do. I'll show you something. I'm going to show you some perspective using a laser scanner. That's what I'll do next. I'm going to add that to this video so that you could see how perspective has absolutely no bearing on the size of the thing that you're actually measuring. I see the curve chart here. Let me make one mention. The next video I do is going to really go into curvature again. I've addressed this before, but think that I'll just mention it here since I'm in the process of making a video. Nobody is addressing this, that theta, that angle. And you notice all of my results, that's what I'm reporting to you. In other words, my theodolite is here. I'm looking out in this direction. So if my theodolite is here and I'm looking out at a lighthouse or a tall building, etc., I'm reporting this to you. And that's the inclination of the plumb lines. I've tried to make this point before, and I'm not sure I'm getting it across to most people, but I sure am trying. But again, I'm going to discuss that more in another video. All right, so that's what I'll do next. I'm going to show you some laser scanning of a bridge, and you'll see how you're going to see the visual of the bridge where I'm set up. You're going to see the bridge getting smaller and smaller the farther away you go, just like any of these pictures. All these pictures showing how things get smaller the farther away they are in appearance. That's all. It's just in appearance. That doesn't mean the gauge of this railroad track is decreasing. Otherwise, you'd have a train derailment. So again, if perspective means this much to the flat Earth, you've got to figure out what it really means, literally, beyond appearance. Because really, that's all it's about, is appearance. This is a visual thing. This does not make the Earth flat. We can measure the curvature quite easily. So, all right, enough of that. I'm going to get on to adding a little bit about 3D laser scanning, which isn't even a theodolite. It's a whole different technology that makes measurements, and perspective doesn't affect it. All right, so you just saw a little video clip, and now you're looking at the laser scanning results. We're talking about many, many thousands, perhaps millions of laser scanning three-dimensional points. And as you can see, perspective has no effect on those measurements, whether they're very close in this direction or from across all the way down to here, hitting all of these members of this bridge. All right, this is going to be the final moments of the video, I think. You just saw a video clip of the scanner in operation on this side of the river, scanning this part of the bridge. You can clearly see the size of these bridge structural components. They do not literally change in size. They are the same size, even though perspective would have these things appearing smaller and smaller the farther away you go. But we can zoom up to them and literally measure dimensions. There is a measuring tool in here. I should have, here it is. If I start making measurements, I'm going to find out that, all these sizes are the same. I mean, I don't think I need to go through any more of that. So anyway, that's 3D laser scanning. That is how we do a lot of measurements these days. And that's it. It's getting late. I'm getting tired, and look forward to the comments and maybe some conversation about, if you have any questions basically on anything I've presented in the video. I'm happy to answer you down in the comments. So I'm going to say goodnight and see you next time on the next one, on the next video. All right, take care. Bye.